In this lecture, in this video, I want to describe to you the first unsupervised learning method that we'll cover. In fact, this is the main unsupervised learning method that we'll cover. Autoencoders are kind of unsupervised learning, but that we actually train them as a supervised learning setting. So Hopfield networks are unsupervised. So the goal is to look at our first unsupervised neural learning method and find out about Hopfield Energy. So here's the idea. It's all about it. Hopfield networks create what we call a content-addressable memory. So to describe what that means, fill in the blanks here. You've got this first one. Two L's, intelligent. The next one. I expect you put an LE there. What about this next one? So if those were your answers, good for you. You have a well-functioning brain. What you did is you took a partial pattern and you filled in with the most likely completion. And because those are patterns that you recognize in your memory, you can fill in even when there are errors. So take these for examples. 1, 2, 3, 8, 5, 6, 7, 2, 9. Of course, it should be, or you can infer that it should be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or this one, neuroscience. It should be neuroscience. Or this one should be Waterloo. So what you're doing is you're looking at this pattern and you're actually recognizing that it's very similar to a different pattern, and you're able to correct the error. So these are both the filling in or finding the clear or correcting errors. They're both essentially recognizing the closest pattern from your memory. So a content-addressable memory, or a CAM, is a system that can take part of a pattern and produce the most likely match from the memory. In 1982, John Hopfield published a famous paper. John Hopfield is one of these people who was largely said to be one of the fathers of neural networks. And so there's what the paper looks like, at least the title: Neural Networks and Physical Systems with Emergent Collective Computational Abilities, 1982. So it's fairly early on in the neural network business. So in that paper, Hopfield proposes a method for using a neural network as a content-addressable memory. The network learns the patterns and converges to the closest pattern when shown a partial pattern. So I'm going to describe to you the main content of that paper. So here I have a network of 6 neurons. Now you'll notice this is already different from our previous neural networks, because this is a recurrent network. We haven't talked about recurrent networks yet, but they have connections going both ways. So every time there's a double arrow, it's actually, you can think of it as 2 connections going in either direction. So one going in this way and one going in that way. That's what the double-sided arrow means. Although we're going to assume that the connections going in opposite directions are actually equal weight, the same weight going in either direction. So anyway, all these weights, I'll just say Wij is the connection strength from node I to node J. And we're going to assume, for the most part, Wij equals Wji. That's one of the assumptions that's made in that paper by Hopfield in order to arrive at the theoretical results that they do. Although they also say that you can relax that constraint and most of the things still work. Okay, so now each node in that network will take on a value of +1 or -1. So they're really just flip-flopping back and forth between those 2 different states. So you can say x sub j is an element of -1 or +1 for j equals 1 to n, or n is 6 in the case of that little diagram. There can be +1 or -1. We can also design our network to be ones and zeros. So you can think of the state of the network being a binary string of length n. So I'll just put a quick note here that there is an equivalent derivation for x being 0 or 1. Okay, so you can, all the formulas I'm going to write down soon, you can just wrap the x inside a simple little remapping to make 0, 1 map to -1, 1. Okay, now, suppose each node wants to change its state according to its input. So in particular, node xj wants to set itself to -1 if the sum of its inputs are less than some threshold. Oops, j not equal to I. So x, I, w, I, j are going to be, if they're less than some threshold. So I'll talk about that in a second. So what I have here is the sum of the inputs coming from all the other nodes, xi. And of course, we don't have, well, not of course, I'm saying that we don't have each neuron feeding back to itself. So j is not equal to I. But the incoming current from all the other neurons, if it's less than some threshold, which I'm just calling -b sub j, then we set the node to -1. Otherwise, we set it equal to 1. Okay, so for now we're going to, for the next little bit of the video, I'm just going to assume that those b's are 0. Okay. Okay, so if we have a pattern that we'd like the network to recall, we could set the weights so that running the network according to this update rule for the x's will, like the node values will change. They'll kind of flip back and forth between +1 and -1, but eventually we'd like them to settle on the pattern that we want it to memorize. Okay, so how do we set the weights to achieve that? So here's one idea. We set the weight from I to j to be positive between any two nodes that are in the same state. So for example, well, I'll show you an example in a second. And we set the weight to be negative between any two nodes that differ. Kindergarten writing. Not that there's anything wrong with kindergartners. Okay, so here's the example. I've got this network with this Hopfield network with 4 nodes, and it's all connected, and I don't even bother with the arrows because I know that every connection goes both directions. So looking at between x1 and x2, those are opposite sign. So I'm going to just say, let that weight be -1. So my weight matrix, first of all, it's going to be zeros on the diagonal because the nodes don't connect to themselves. Between node 1 and node 2, we have a weight of -1. Between node 2 and node 3, they're both, again, they're opposites. So we have node 2 and node 3 is -1. Between node 2 and node 4, that's this connection here, they're both negatives, so we want a positive weight between those two. 2 and 4, 1 and 1. Between nodes 1 and 3, they're both 1s. And what else am I missing? Between 3 and 4, they're opposite. 3 and 4 are opposites. What's this one up here? That is between 1 and 4. They're opposites. Okay, I think I filled it in correctly. So that weight matrix, if you could set those, you could erase the +1s and -1s from that network, from the nodes themselves, set them to something random, and then you just apply apply this update rule up here, and they will, the nodes will kind of snap around +1, -1, but eventually, given those weights, they should arrive at that state that I have in here. Or actually, it could arrive at the opposite. So all the 1s become -1s and the -1s become 1s. Those two states are basically considered to be equivalent. Okay, but I could also set, I could make an error. I could set that one, oops, I could set this one to +1, for example. So there's an error. And now run it. And there's a pretty good chance that it will recover that and change that +1 back to a -1. So that's the idea behind a content-addressable memory. Seems like a good time for a joke. I can picture in my mind a world without war, a world without hate, and I could picture us attacking that world because they would never expect it. Okay, so that's great. We can set the connection weights for one pattern. What if we have multiple patterns that we want this network to memorize, so that if we set the network state close to one of them, it'll snap to the correct one. If we set the initial state close to a different one, it'll snap to that different one. So how can we find the connection weight matrix W that works for a set of memories that we want to encode? So I'll describe Hopfield's answer. So given M target network states, which I will call X superscript 1 to X superscript M, we choose our connection weights like this. The weight from I to J is 1 over M times the sum, S equals 1. So we're going to add up over all the patterns. X so for I not equal to J. So the weight from I to J is going to be basically running through all of those patterns and looking at the two different states of the nodes that weight is between, and basically adding up how many times they're in the same state and how many times they're in opposite states, and basically averaging across those. So Wij is the average coactivation between nodes I and J. Okay, and then we set Wii, the diagonals, to 0, which, incidentally, can be written as in the same format as the formula above. Xis, Xis, and then -1. because whatever xi is, whether it's a +1 or -1, multiplying it by itself is just squaring it, so you always get 1. So this first summation adds up to m, because it's adding up over m different samples. It's 1 + 1 + 1 + 1 m times. Divide by m gives you a 1 minus 1. So anyway, you can work out if that was too fast for you, then I guess you could play this back in slow motion, or you could just think through it yourself. Okay. Now, notice we could put all that in sort of a vector matrix product kind of way. This is kind of one of our habits, right? When you see like all these, or at least when I see all these subscripts in these formulas, I like to try to reformulate it into a matrix formula. So I could rewrite that thing as W equals the sum, sum 1 over m times the sum over all the samples of xs, now that's a vector, times xs transpose minus I. So I'm claiming that this sort of takes care of all of the ij's at the same time. So I could rewrite that. I like to draw little pictures. So it's kind of like a sum over s of xs, which, I guess I'm using column vectors right now. Maybe I'll do it this way. I'll go back to row vectors. I should be explicit. xi is, I guess I'll use column vectors here. So it's, I don't see how long they are. I'll just say n by 1. Okay, so we have column vectors. The state of the network is a column vector. So then this product here, I can sort of draw it as a column vector times transpose of the same vector, so it's a row vector, then minus the identity. So this thing here is what we call, we've called it an outer product, but it's like inside that summation, it's an outer product, or you can call it a rank 1 product. It's basically a matrix with really just 1 degree of freedom. So I could rewrite that whole summation. It's 1 over m, a matrix plus a matrix plus each one of these matrices, I've got m of them. M rank 1 matrices. Each one of those matrices comes from this outer product of xs with itself. And then we subtract the identity. Maybe I'll draw the identity like this. Okay. So that just shows an alternative way of computing it. So we have our connection weights. This method works best if all of the patterns are mutually orthogonal. I see now I've got these little vector symbols here. I'll get rid of those. And I want brackets there. Okay. They work best, this method works best if they're mutually orthogonal. They don't have to be. And I think in the exercises or your assignment will be a question, a little proof about how orthogonality factors into why those weights work. In fact, I've told you how to compute the weights. I haven't told you really why those weights work. So that's what the exercises are for. So I'll demonstrate this to you in a bit. But for now, let me push forward with the theory so that we can interpret it properly. Hopfield in the paper recognized that there was a link between these Hopfield networks, or between these content-addressable memory networks, and the Ising model in physics. So what's the Ising model in physics? It has to do with a bunch of dipoles, magnetic dipoles. They're in an array. And now they can be up or down. They're very specific, up or down. Just think of it as like magnets with a north and a south pole. And if one flips over, that sort of changes the magnetic environment for its neighbors. So its neighbors now have a slightly different magnetic field around them, and that might cause them to flip. And so you can cause this cascade of flips. If you flip one, you can sort of cause this reconfiguration of the lattice. But the low energy state of any dipole depends on its neighbors. And so if it changes, it might change the state of its neighbors. If its neighbors change, it might change the state of its own dipole. So you can see they're all sort of linked together. So it's not a big leap to imagine how that's similar to this network, where each node is connected to its neighbors, and each node's state is influenced by its neighbors, but it also influences its neighbors. And what it's looking for is a low energy solution to a state of the network, or a state of the lattice. This lattice, the dipoles will flip around up and down until they sort of snap into a state where any single flip of any of the dipoles will actually cause an increase in potential energy. So it's looking for this minimum energy solution. So Hopfield realized this, saw this link, and said, I should create an energy that's based on the same idea of the energy depends on how much consistency or inconsistency there is between the nodes that are connected. Or basically, you get higher energy when there's an inconsistency between, or a tension, I guess, between nodes that are connected. And so the inconsistency will be, okay, what are the two node values, and is the weight between them consistent with those node values? If they're opposite signs, you want a negative weight. If they're the same sign, you want a positive weight. That's the idea behind the energy. So for our neural network, we're going to again assume that W is symmetrical, and I'm going to define this energy. So the energy of the network is going to be -1/2 times the sum over all of the nodes. In fact, this is a double sum. But I'll just write it as a single sum like that. Xi, Wij, Xj. So this is basically what you expect. You've got Xi and Xj, and they could be the same sign or opposite signs, and you're multiplying them by Wij. So that triple product there is going to contribute to the energy. So if that results in a negative value, it's going to increase the energy, right? Because there's this minus sign out in front. So if Xi and Xj, for example, are opposite signs, and Wij is negative, that'll give you a positive value of that triple sum, which means it'll make the energy go down. Okay, so you can think through the different cases there and see that what we're looking for is that consistency. This energy is measuring the amount of inconsistency between those node states and the connection weights between them. And we also say that there's an energy cost to each node being on or off. So if node J is on, it reduces the energy by B sub J. If node J is on, well, on or off, whatever. I can't remember what I said first. But whether Xj is +1 or -1, it's going to add or subtract B sub J. B sub J can be positive or negative. So this is a way of sort of measuring the amount of energy, sort of internal tension in the network, if you like. This can be rewritten as -1/2 x transpose wx. Again, here x is a column vector. Minus b transpose x. And in all of this, I'm assuming the diagonals of the weight matrix are 0. So this thing, which I will put a ceremonial box around, is called Hopfield energy. Named after John Hopfield. So just like in nature, as nature operates and things move around, it kind of has this natural tendency to minimize energy. So if you have a marble in a bowl, it's going to roll, and basically the energy will dissipate, and it will eventually end up in its lowest energy state, lowest gravitational potential energy state. So nature just has a way of automatically minimizing potential energy. So if we were to minimize energy, how would we go about doing it? Well, let's look at that Hopfield energy and do gradient descent on it. So I would say, in terms of, let's assume our connection weights and biases are fixed, and our job is to change the node values, the x's, to minimize our energy. Well, what I would do is I would take the gradient of my energy with respect to the node values, and I would use that for gradient descent. So the gradient is, and you can work out the details, but I'll just write it down, negative sum over I, not equal to j. This is now a single sum of x, I, w, I, j. So j is, you can evaluate that the sum is over I, and so you end up with something with index j. And then minus b sub j. Okay, so this might look familiar. Using that gradient for gradient descent, if I want to find the states x that would minimize the energy, I can push my states, my x's, in the direction opposite that gradient. So I could say dxj by dt equals the negative of that gradient. And I could even throw in, I guess I could do that. Throw in step size. J not equal to I, xi, wij, plus bj. See, the minus signs are changed to pluses now. Okay, so this, and when I say this might look familiar, it's because it sort of comes from the update equations I wrote up above, which I'll rewrite here for the states of x. Let me just rewrite it here. So basically, if the input current is negative, then we set the node to -1. If the input current is positive, we set the node value to +1. So it's like a threshold network, threshold activation function, if you like. Moreover, we could, so if we wanted to do gradient descent on the connection weights and biases, we could do the same thing. We could take the gradient of E with respect to wij, the partial derivative of E with respect to wij. What would that be? Looking up here, basically be, it would just pull out the one term of that double sum that has the xi and xj in it. Now since there should be a 1/2 there, right? Okay. My notes don't have the 1/2, but I'm pretty sure there should be a 1/2 xi xj. But it doesn't matter because we're just going to, when it comes time to doing gradient descent, that 1/2 just gets absorbed anyway. So that's the gradient. If we want to do gradient descent, we take a step in the direction opposite that gradient. So kappa xi xj for I not equal to j. Okay, so that is consistent with the formula that we had that I had written, that Hopfield suggested, would be the set of weights that would be appropriate for memorizing a collection of memories. It's basically this one here. Except this is kind of an iterative way of computing that. So it's like we're going through the different the states of the two different nodes, I and j, over our data set and sort of incrementally changing our weight. Now for bias, same sort of thing. We go up and we take the gradient of e, or the partial derivative of e with respect to b sub j, we get negative x sub j. Which is why the gradient descent update would just be kappa times the negative of that. So that's Hopfield networks. The reason I bring it up, why I think it's important, is because this notion of Hopfield energy drives a lot of the theory and the practice behind unsupervised learning. We don't have an output, so we can't compute a loss, and therefore we can't compute gradients and things to update our connection weights and biases by. Instead, we come up with this idea of energy, and we want to minimize energy. That basically gives us something to optimize. Now we can start changing things, change our network state, change our connection weights and biases to minimize energy. And that's what drives a lot of unsupervised learning, Hopfield energy.